Now we will observe different properties of Smith chart. Now how to interpret this Smith chart and how to calculate different parameters using Smith chart. Now we will observe using a real practical Smith chart. This is the Smith chart that what we have. You can observe this is a complete Smith chart, and on this Smith chart you have different circles. Some of them are complete circles and some of them are partial circles. Just what I do is I will maximize this Smith chart to get a clarity. Just observe this Smith chart. So in this Smith chart you can have different circles like this. This is a very smallest circle that what you are observing, and this is a little bit larger than that one. Like that you have different circles. All these are complete circles, right? So these complete circles are meant for, clearly once again I am saying, these complete circles are meant for resistance, a normalized resistance. And already we have drawn a few circles on our board, that the exactly center circle which is passing through the center point is meant for r is equals to 1. So this is the value r is equals to 1. Now the circle which is passing through this particular point, that what I am showing now using the pointer, is resistance 1 circle. That resistance is the normalized resistance. So this circle is complete circle which is meant for a normalized resistance circle. Now if there is any circle which is not complete, what you have to do is you have to complete that one with the help of a pencil, because it is not possible to print all those circles on this chart. You have to completely draw the circle whenever it is necessary, right? Now observe this chart, and before going to that, what I do is just I will show you how to hold this chart. This is a position, how to hold this chart, that the meeting point of all the circles must lie to the observer right side. So right side to the observer point, and the remaining part must be at the left side of the observer. Right here I am observing the chart, that's why as this is the right side point that what I have to hold, and this is the left side point that what I have to place, right? So here clearly all these circles are resistance circles that what we have, and the values of those resistance circles are printed on horizontal line. Now if you observe that one, so this is the extreme right point that to the observer. This extreme right point is meant for r is equals to infinity circle. R equals to infinite circle means a circle with zero radius. Zero radius is completely a point. So here that's where I am showing is said to be the r is equals to infinite circle, right? And similarly you can observe r is equals to 50 circle, r is equals to 20 circle, r is equals to 10 circle, r is equals to 5 circle, r is equals to 4 circle, and all these r circles means resistance, normalized resistance circles are complete circles. Similarly you can observe different partial circles. Just you observe here, this is a small partial circle. Randomly I took this circle. This is not completed here, but you can complete that one with the help of a pencil up to this particular point. So this is equals to x is equals to 3 circle. So this x is equals to 3 circle is meant for normalized reactance, and it is also a positive, as I said. So while we are drawing these circles, so the upper part of our horizontal line, this is a horizontal line that what we are supposed to consider, and this is meant for gamma r. So the upper part of the horizontal line is always meant for positive reactance. Just you observe the positive reactance. So all these values which are printed here, that where I am showing with the pointer, so all the values which are printed here are meant for positive reactance. And you can take any value of the reactance. This is a value of plus 50, and this is a value of plus 20, and this is a value of plus 2.0. So whenever it is necessary, what you are supposed to do is you are supposed to take or observe. Now the partial circles which are drawn below the horizontal line, that what I am showing now, so this is a partial circle which is below the horizontal line, this is another partial circle which is below the horizontal line, all they are meant for negative reactance. That let us take an example. If you are taking a negative reactance of 2, that you need to identify this circle. This partial circle is meant for a negative reactance of 2.0. This partial circle is meant for a negative reactance of 1. This partial circle is meant for a negative reactance of 0.5. And as I said, wherever it is necessary, you need to complete this circle, and you have to draw up to this particular point, that is where x is also equals to infinite. Now at this extreme point, so we found r is equals to infinity and x is equals to infinity. That's why this particular point is always said to be the point of open circuit. Clearly remember that one. whenever you are observing this point, that is not up to this point, don't go up to this line, just at this line you are supposed to stop, right? At this point r is equals to infinity and x is equals to infinity, which corresponds to, this is a point of open circuit, and exactly opposite to this line at this point, so you are supposed to say that this is point of open point of short circuit. Since it is point of open circuit, this is said to be the point of short circuit. Now while you are moving from center point to the point of open circuit along this line, clearly observe what is the line that what I am showing. So along this line the voltage is always maximum. As this particular point is open circuit point, always you will get the maximum voltage, right? So now here clearly it's from center point of the Smith chart to the extreme right point, that is nothing but our point of open circuit. Whenever we are observing this line is said to be the maximum voltage line or minimum current line. Similarly, from the center point of the Smith chart to the extreme left is nothing but point of short circuit. So when we are moving from center point of the Smith chart to the extreme left point of short circuit, that particular line is always said to be the V minimum line and I maximum line, that the current will be maximum along that particular line. Now observe different properties of our Smith chart again. So once again, just I will recap. The complete circles are always resembles the resistance circles, and a partial circles are always gives us the reactance circles. In those reactance circles also what we have is, it's a positive reactance, they are above the horizontal line. Negative reactance, they are below the horizontal line. This is our point of open circuit, this is our point of short circuit, and this particular line is said to be the maximum voltage line, and this particular line is said to be the minimum voltage line. So they are the just basic circles and lines on our Smith chart, and observe you have 4 more scales around that Smith chart. Just you observe that there are 4 lines around the Smith chart. These 4 lines are meant for only measuring purpose, they are scale. Now observe different circles which are drawn around the Smith chart. As I said, the maximum boundary for our Smith chart is r is equals to 0 circle, that is this is r is equals to 0 circle. Up to this one only we are supposed to consider any value of our impedance. Now above that one we have 4 more circles. These 4 more circles are meant for measurement of angle or measurement of wavelength, that you can measure the angle in terms of degrees, in degrees for the transmission or reflection. Now, similarly, you can measure the wavelength in one direction or another direction using these 4 scales, right? That's why these 4 circles were drawn around our Smith chart. Now clearly observe the first circle that what we have is for angle of transmission, that the values here clearly which are printed here are meant for angle of transmission coefficient in degrees. And similarly here also you have another scale just above that one, that is angle of reflection coefficient in degrees. So if you are calculating transmission coefficient or reflection coefficient on this chart, we can use these 2 scales for the measurement of angles, as the reflection coefficient or transmission coefficients are complex quantities that can be represented as r angle theta. That angle theta can be measured using these 2 scales. Similarly, the wavelength can be measured using the third and fourth scales. The third scale is the wavelength in one direction, the fourth scale is wavelength in another direction. So these 4 scales are useful for measurement of angle as well as wavelength. Now clearly just you observe the basic structure. It will have a complete chart up to r is equals to 0 circle with along with our x circles, right? After that one we have 4 more circles. These 4 more circles are meant for clearly measurement of angle and measurement of wavelength in different directions for different parameters. Now observe, if you are taking a rotation, here since this chart is like just a circle, you can take the rotation along the chart or around the chart. So if you are taking a rotation around the chart, so you can take either clockwise direction or anti-clockwise direction. Right? If you are taking anti-clockwise direction, what is the meaning of that one? If you are taking clockwise direction, what is the meaning of that one? Just it is simply an imagination that you are supposed to take. We have a physical transmission line. That physical transmission line is connected with a load at the load end and source at the source end. Let us imagine this is the source end and this is the load end that what we have. Whenever we are calculating the load, you are at source, you are moving towards load and you are calculating the impedance there. right? Whenever you are calculating the input impedance, you are at load and you are moving towards the generator. These two are the two cases that what you are supposed to imagine. For a physical transmission line, you may be at load and you are moving towards the generator, or you may be at generator and you are moving towards the load. If you are moving towards the generator, clearly remember you are supposed to take the clockwise rotation on our Smith chart. Just observe here, that is wavelength toward generator is, the arrow mark was given like this, that whenever we are taking a rotation in clockwise direction, that it is moving towards generator, that from the load you are moving towards generator. Similarly here, this is wavelength towards load, that you are moving towards load from source, that is in anti-clockwise rotation, anti-clockwise direction. So clearly you are, one more point you are supposed to remember about this Smith chart is, whenever you are considering a rotation in clockwise direction along this Smith chart, then it is corresponds to moving towards generator, and whenever you are taking a rotation in anti-clockwise direction, you are moving towards load. And at how much distance you are moving and where you have to stop, that's purely depend upon the length of the transmission line. And so how to calculate that length, or how to observe that wavelength, using these scales. The scales what we have around the Smith chart are useful for measurement of the length, how much we have travelled along the transmission line. So the correlation must be like this, you have to imagine like this, we are moving on the transmission line is equals to taking a rotation around the Smith chart. We are moving from load to generator, taking clockwise rotation on the Smith chart. We are moving from generator to load, taking anti-clockwise rotation on the Smith chart. So this is a very simple point you are supposed to remember while solving the problems. Now, how much distance it covers for one rotation, that is also one of the important point you are supposed to remember. That if I am taking a complete rotation along the Smith chart, then a complete rotation along the Smith chart always corresponds to lambda by 2 distance travelled on a transmission line. That if I am taking a 360 degrees rotation on the Smith chart, that which corresponds to a lambda by 2 transmission, whatever it may be the direction. If you are taking clockwise direction, that you are moving towards a generator. If you are taking anti-clockwise direction, you are moving towards a load. Whatever it may be, that the complete rotation always corresponds to lambda by 2 distance travelling. For your understanding, I will give you one example. I have a transmission line with length lambda. Let us take a transmission line with length lambda. Where I am at the load. Now I have to move up to the generator. So as I have to move up to the generator for a distance of lambda, what I have to do on the Smith chart? I have to take a rotation on the Smith chart in which direction? Clockwise direction. So I am at the load, right? I am moving towards the generator. As I am at the load and I am moving towards the generator, I have to take a clockwise rotation on the Smith chart. The clockwise rotation corresponds to how much distance on the transmission line? Lambda distance on the transmission line. I completed one complete rotation in clockwise direction. So how much distance I have travelled? Lambda by 2 distance I have travelled. I have to take one more rotation to complete our travelling, right? So one more complete rotation corresponds to another lambda by 2. So lambda by 2 plus lambda by 2, which is completed on the transmission line, which is equals to 720 degrees rotation on the Smith chart in clockwise direction. So this is a simple correlation that what you are supposed to take, right? Whenever we are traveling from load to generator, take a clockwise rotation. So how much distance, how much angle you are supposed to take a rotation, that's depend upon the length of the transmission line. The length of the transmission line, lambda by 2, corresponds to 360 degrees. So if it is lambda distance, 360 into 2. If it is 2 lambda distance, 360 into 4. Like that, you have to connect or you have to correlate the angle of rotation on the Smith chart with the length which is travelled on the transmission line. So once again, I will give you with the Smith chart. So just start here. Now where I am is at this particular point. I am assuming that I am at load. Now I am travelling towards generator. Now completely I am taking a rotation around the Smith chart in clockwise direction. Right, as I am moving towards generator, the clockwise direction rotation I am considering. If I stop at this particular point, how much distance I have travelled in terms of wavelength? 0.25 lambda I have travelled. It's up to 0.25 lambda I have traveled on the transmission line, that is lambda by 4, right? Now I continued my traveling, so still I am continuing my traveling, that is I completed one complete rotation. One complete rotation corresponds to 360 degrees. I started at this point and stopped at this point. There is a complete rotation I completed, which is equals to 0.492 of this particular one is 0.5 lambda. 0.5 lambda corresponds to lambda by 2. So clearly this circle will gives you a wavelength in clockwise direction, that is we are moving towards generator. Now similarly, if I am moving towards load, now let us consider the reverse case, that if I am moving towards load from the generator, let us take, this is the point what I am considering, that is at this particular point the generator is there. From the generator I am moving towards load. Now if I am moving towards load, just you observe, so what happens to this lambda value? The lambda value is further increasing and it reaches 0.5 lambda. From this point 0.25 lambda to 0.5 lambda, what you will get is 0.25 lambda, that is nothing but lambda by 4. And from this point, so 0 to 0.25, which corresponds to lambda by 4. Total, the complete rotation in the load direction is also equals to lambda by 4 plus lambda by 4, which is equals to lambda by 2. So whatever it may be the direction of rotation, that either clockwise rotation or anti-clockwise rotation, that is towards the generator or towards the load, one complete rotation is always corresponds to 360 degrees, is always corresponds to lambda by 2 traveling on the Smith chart. So whenever you are supposed to calculate different parameters on the transmission line, you must correlate it. That's how much length I have for the transmission line and how I have to convert that one into the degrees. As you are supposed to take angle of rotation here, you are supposed to convert that transmission line length into the degrees. Now these are the some basic parameters that what we have related to our Smith chart. Now I will give you how to represent a particular impedance, load impedance. And as I said, that load impedance is not a normal load impedance, that is normalized load impedance. So here what I do is just I will give you how to represent a load impedance. So as I said, this particular chart is calibrated for normalized values. You are supposed to consider the normalized load impedances or input impedances, that is the impedance is divided with the characteristic impedance of our transmission line. So as an example, just I will give you a simple example. Let us consider a load impedance ZL is given as 100 plus Z200 ohms. Once again, the load impedance is given as 100 plus J200 ohms and the characteristic impedance of our transmission line is 50 ohms. Now what is the normalized load impedance? 100 plus J200 divided by 50, which is equals to 2 plus J4. Now just you examine what is the normalized load impedance. In that normalized load impedance, what we have is resistance value 2 and reactance value as plus 4. That is clearly a positive reactance. Now I will tell you how to represent those two and how to identify the load impedance on our Smith chart. Now to represent our normalized load impedances, that is 2 plus J4, we are supposed to observe resistance value, the resistance is equals to 2 and the reactance is plus 4. Now observe our Smith chart. On the Smith chart, that what we have is different resistance circles. Among those, this is the line that what I am showing, exactly the line what I am showing is R is equals to 2 circle. What you have to do is you have to take a pencil and highlight this complete circle. Now this is the complete R is equals to 2 circle which is supposed to identify for that particular normalized load impedance. So this is not only the part, that we have one more part, that is we are supposed to observe normalized reactance also. What is the value of reactance? Plus 4, right? So for plus 4, just you observe the reactance values, that since it is a positive, the value what I am considering is above the real axis. Now it is plus 4, right? Highlight this plus 4 circle. Now the intersection point of our R is equals to 2 circle, that is nothing but this highlighted circle, and X is equals to plus 4 circle, that is exactly this point. So the point that what I am mentioning is nothing but the load impedance. And once again clearly remember, this load impedance is the normalized load impedance. So to observe the normalized load impedance, what we did is we normalized the value and we observed the resistance value and highlighted the circle. we observe the reactance value, highlighted the circle. The intersection point of the resistance and reactance circles is nothing but the load impedance, that what we observed. Similarly, you may have one more impedance. I am considering here, it is input impedance. The input impedance has 50 plus J100 ohms, and the characteristic impedance of our transmission line is 50 ohms. So if you are observing that particular input impedance on the Smith chart, you have to normalize that one. Whenever it is normalized, what you will get is 1 plus J2. So the resistance circle is 1 and the reactance circle is plus 2. Once again, I will try to represent those two circles on our Smith chart. Just you observe here, on this Smith chart, the resistance circle for 1 is this circle, that completely highlight this circle. Now similarly, the reactance circle for 2 is this circle, right? So the intersection point of R is equals to 1 circle and X is equals to 2 circle is this one. It's exactly the pointer locates the input impedance or 50 plus J100 ohms, right? Similarly, I will give you one more example with negative reactance, and with that one I will conclude how to represent an impedance. Let us consider one more impedance as 50 minus J100 ohms, that I have to represent 50 minus J100 ohms with the characteristic impedance 50 ohms. Then if you normalize that one, it will becomes 1 minus J2. Here the resistance circle is 1 and the reactance circle is minus 2. Clearly observe, don't take that one as plus 2, it is minus 2. Whenever it is minus 2, that will comes under or the below the real line. So just you highlight R is equals to 1 circle, X is equals to minus 2 circle, the intersection point of those two is our impedance. I will show you that one on Smith chart, that this is R is equals to 1 circle and our X is equals to minus 2 circle will lies here. That this is our R is equals to 1 circle and X is equals to minus 2 circle is here. The intersection point of those two circles, that is where my pointer is locating, then it is said to be 50 minus J100 ohms. Exactly, you are supposed to identify our impedance at this particular point. This is a very important and basic point related to our Smith chart, that whenever we are considering a Smith chart, you are supposed to identify where the given impedance is there. Whatever it may be, that may be load impedance or that may be our input impedance. If you are identifying load impedance, imagine that you are at load. If you are identifying input impedance, imagine that you are at input, that is nothing but our generator. So depending upon the conditions, you are supposed to calculate different parameters. Now I will give you just a very simple parameters like reflection coefficient, standing wave ratio, and how to calculate those two parameters on our Smith chart, right? For that, what I do is just I will give you how to calculate the reflection coefficient initially, and then how to calculate the standing wave ratio. That's using that reflection coefficient circle. That's a very small circle will be there. With that circle, how to calculate a standing wave ratio also I will give you with a simple example. Let us take, we have a load. As we discussed, always the reflection coefficient will be at the load only. That in the problem, the load impedance will be given to us. So whenever the load impedance and characteristic impedance are available, you can calculate the reflection coefficient using our formula, ZL minus Z0 divided by ZL plus Z0. But here we are not supposed to use any formula. Instead, we are supposed to use our Smith chart. So the main and basic step is to identify the load impedance. Here, randomly I will consider a particular point as the load impedance. On our Smith chart, I will consider a particular or a random point as the load impedance. Now, with that one, I will start our problem. Now, on our Smith chart, let us consider this point. That this point always represents R is equals to 1 circle and this X is equals to plus 1. So, this may be 1 plus J1 ohms as the load impedance, that what I am considering. Now, what you have to do is join our origin point, that is the center point, with this point, that is nothing but ZL. Now, draw a straight line. Clearly, from the center point to the point what I am identified as ZL, just you draw a straight line and extend that straight line up to R is equals to 0 circle. That what I am saying, clearly identify. The first and most important step is to get ZL location, and I am assuming that this is the ZL location, 1 plus J1 ohms is the ZL. Now the second step is to draw a straight line from the center point to the ZL and extend that line up to R is equals to 0 circle using a scale. Just you are drawing a straight line that which is passing through ZL from origin to r is equals to 0 circle. This particular line is enough to calculate our gamma. Now, how to calculate gamma? A simple formula is there. Let us name this one as origin O. This is ZL, and the point where our straight line meets our r is equals to 0 circle as Q. Right? Now, calculate OZL length, calculate OQ length, then the formula for our reflection coefficient is OZL divided by OQ angle POS or QOS. This is Q, right? Angle QOS. Now, what is S, sir? S is nothing but, for time being, just you remember this real axis as S line. Right? For time being, later I will give you what is that S. For time being, just you remember this real axis as S line. Now, once again I will say how to calculate this gamma. Very simple. Just you identify ZL, then connect our origin with ZL, extend the line of OZL up to point Q, then calculate OZL, calculate OQ, OZL divided by OQ angle QOS. That angle QOS is nothing but the angle between the line that what we have drawn and real axis in clockwise direction. This is our simple gamma formula. And the second step is just you draw a circle with O as center and OZL as radius. Always just you take a compass and draw a circle with O as center and OZL as radius. That particular circle is said to be constant gamma circle. On that circle, always the magnitude of gamma is constant. Here, not only at this particular location, if you calculate here, after drawing the circle, if you calculate this OZL, it's not ZL exactly, up to the radius of the circle that what we have drawn and the distance between this point and outermost circle, take the ratio of them, then also it will be equals to the gamma what we have calculated earlier. So, the circle that what we are drawing, or that what we have drawn as OZL as radius and O as circle is called as constant gamma circle. Now, using that circle easily you can identify standing wave ratio. How to identify the standing wave ratio using that circle? Just observe. Now, watch our Smith chart. Just you observe where our circle meets the real axis. That whenever I am drawing a circle with this radius, the circle may lie like this. The circle may be like this. So, that this is the imaginary circle that what I am drawing. So, actually this is not existing here. You can imagine that this is a circle that what is existing, that OZL as radius and O as center. After drawing this one, this circle is passing through the real axis, right? So, on this real axis, identify the value of resistance. That resistance will be somewhere here. I am not saying radius, just clearly identify the value of resistance where the circle meets our real axis. So, whenever the circle meets our real axis, so definitely some resistance value will be there. That resistance value is nothing but the standing wave ratio. So, it is very easy to calculate using our Smith chart. What are the parameters which are required? So, what are the tools which are required are just a pencil and scale. Using that pencil and scale, usually you can draw the circles that what we have, or draw the straight line that what we have, measure the distances that what I said, OZL, OQ. So, take the ratio of OZL to the OQ and measure the angle. Measurement of angle is also possible with the scales that what we have here. That easily you can measure the angles that using these scales. So, no need of our protractor also, right? Then you will get our reflection coefficient, and then observe the radius where our circle meets our real axis, then it is said to be the standing wave ratio. So, these two are the two simple parameters what we can calculate using our Smith chart. Now, we can calculate the input impedance or different problems which are related to the Smith stub matching, that may be the single stub or double stub, using the same Smith chart. That will be continued in our next session.